Hello and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm John West, your host for today. I work at the Texas Advanced Computing Center, and I'm also an ACM member and vice chair of the ACM Special Interest Group on HPC. For those of you who may be unfamiliar with ACM or what it has to offer, let me tell you a little bit about it. ACM is the world's largest computing society. It offers educational and professional development resources that grow skills and enhance careers. One way our members stay competitive in the world of computing is by taking advantage of the resources at learning.acm.org, and I encourage you to check out that link after this talk. Before we get started, let me mention just a few housekeeping items. First, the slides will advance automatically throughout the talk. On the bottom panel, you'll find a number of additional widgets and resources. If you experience any problem with slides or audios during the presentation, if you're on Windows, press F5. If you're on a Mac, press Command-R, and that will refresh your browser. Or you can close and relaunch the presentation, and that usually clears up most of the issues. To control the volume, adjust the master volume on your computer. If you have questions during the webcast, and I do hope you have a lot of great questions, please type them into the Q&A box at any time during the talk and click the submit button. I'll organize those as Doug talks, and he'll reserve some time at the end of the presentation to answer questions. This session is being recorded and will be archived and available online. You'll get an automatic email notification when it becomes available. And you can also check learning.acm.org for updates on this tech talk and on other upcoming talks. At the end of the presentation, you'll see a survey open on your screen. I hope you'll take a minute to fill that out. It helps us make the tech talks more relevant and helps us make every talk a little bit better than the last. You can use the Facebook and Twitter widgets on the bottom panel to share the presentation link with anybody in your circles, as well as to tweet comments and questions using the hashtag #ACMLearning. We'll be watching for your tweets. We also have a new community discourse page to continue the discussion after the webcast. And we'll post there questions that we won't be able to get through during today's Q&A session after the talk. So today's presentation is the Exascale Computing Project and the Future of HPC by Doug Kothe. Doug has more than 3 decades of experience in conducting and leading applied R&D in computational applications designed to simulate complex physical phenomena in the energy, defense, and manufacturing sectors. Doug is currently the director of the Exascale Computing Project, and that's what he'll be talking about today. Prior to this, he was the Deputy Associate Laboratory Director of the Computing and Computational Sciences Directorate at Oak Ridge National Laboratory. Other prior positions for Doug at Oak Ridge, where he has been since 2006, include Director of the Consortium for Advanced Simulation of Light Water Reactors, DOE's first Energy Innovation Hub, and Director of Science at the National Center for Computational Sciences. Before coming to Oak Ridge, Doug spent 20 years at Los Alamos, where he held a number of technical and management positions. And Doug is also a member of ACM. Okay, Doug, I will turn it over to you.
Thanks, John, and the folks at the ACM. This is a great way to give a talk. I'm sitting here in beautiful Oak Ridge. It's a great day outside, and I don't have to travel, so thank you. It's an honor and privilege to be here. I'm just going to jump right in and advance the slides here. What I'm going to do is maybe I'll leave it to the audience to ascertain the future of HPC. I'm going to talk about Exascale Computing Project, the U.S. Department of Energy project that I've been involved in. It's a very exciting effort, and I'm going to do my best to get through the breadth and depth of what we've been up to and look forward to questions at the end. So what is the overall goal of the ECP? Basically, we have a mission and a vision. A mission, our reason for existence or purpose, is to develop exascale-ready apps. The applications are going to be poised to solve problems or address problems of national interest. To do that well, we not only need to develop applications, but create and deploy an expanded and vertically integrated software stack. And we need to work closely with U.S. HPC vendors in terms of technology advances that address our needs and requirements, ultimately appearing in exascale platforms. Our vision really is not necessarily the products, but it's the solutions. Our vision is to deliver exascale simulation and data science solutions and innovations. And we're driven in large part by DOE mission problems in technology development, science discovery, healthcare, energy, economic, and national security. So that's kind of our overarching goals and objectives. And I'm going to take you through some more details here. But first, to put this in context, there's an overall initiative in the Department of Energy known as ECI, the Exascale Computing Initiative, and ECP, Exascale Computing Project, is one piece of that pie. Key other parts that are not formally part of ECP, but an important part of our effort overall in terms of the DOE Exascale initiative are 3 system procurement projects known as ALCF3, OLCF5, and ATS4. Lots of acronyms there, but basically the first 3 exascale systems in the Department of Energy system at Argonne, Oak Ridge, and Livermore. On those systems is where we're going to deliver on our apps and our software stack and deliver on our metrics. There are also other selected DOE Program Office investments in the ECI. So the ECI is really the overarching cross-cutting initiative in the Department of Energy, and the ECP is an important part of that. I'm going to talk today about the Exascale Computing Project, but I'll note that these 3 exascale first mover systems are a critical path for our success. We need them to be there on the floor for us to deliver on our metrics. And I'll say a little bit more of that, about that as we go. So we've often talked about a capable ecosystem, which is certainly an expected outcome of ECP, is to work with vendor partners and the procurement projects to ensure we have a capable exascale computing ecosystem. And you can see there's a hardware, software, and application aspect of that, but overall, the system needs to be useful, usable, and affordable. Usable means a software stack that really is amenable to our application requirements. Useful, meaning applications can deliver on DOE mission problems, and affordable, meaning deploying the systems with a cost envelope and resiliency, and those sorts of important requirements needs to be there. So the capable ecosystem is an important aspect of what we're trying to do. As the folks here online probably very much appreciate, HPC computing is hard and really getting harder. Applications need to find more and more concurrency to keep up. And I think there's a good story there. At least that's what we're finding in ECP. Moving data is becoming more and more costly relative to computation. Computation is more or less free these days, so to speak. IOVIS analysis and our data, our workflows are becoming more and more complicated and becoming often the bottleneck in our workflow. The hardware landscape is really diverse. That's exciting for development, but also risky and scary. And so we need to make sure that we're co-designing with our hardware U.S. vendor partners. And there's lots of new programming models to choose from. And so which ones do we choose? Do we bet on them all on one? And so there's lots of choices. So it's not easy, which is really why this project is here, which is to directly address these challenges. In terms of ECP by the numbers, we have been a formal project in terms of DOE since late 2016. We are a 7-year project, so we're kind of approaching our mid-course, 3.5-year timeline. We are fortunate to have a large DOE investment behind us of $1.7 billion over 7 years. 6 core DOE labs have been asked to lead the project. These are traditionally the core DOE labs that have been heavily involved in HPC research, development, and deployment of systems. And so the leadership team is from these 6 labs. And but I'll note that staff from most of the other labs are involved in executing the research. We have 3 technical focus areas that I'll get into, not surprisingly, hardware, software, and application. And in terms of the teams actually executing R&D, there's over 100 of R&D teams that involve not just DOE lab people, but universities and industry. The teams range from 5 to, say, 20, and have really been working over 3 years now, and hopefully I'll be able to share some results. So it is a large project, a large, complicated project that we believe is, at this point, going well, and hopefully I can convince the folks here of that. So this is a notional vision of what ECP is doing. Call it a 7-year sprint to uplift the current roadmap, and it's just not hardware roadmap, but it's apps and software, and get us on another trajectory in preparation for exascale. So an important leave behind of ECP is a sustainable ecosystem, apps that can deliver science and engineering solutions for many years and hopefully decades to come, and a sustainable software stack are really key. So while this is a 7-year project with a definite end and definite metrics, it's really, we believe it will uplift the nation for years and hopefully decades to come with regard to delivering on the science and energy missions of DOE. I'd be remiss not to note the DOE roadmap of two exascale systems, and we are really fortunate in ECP to have some fantastic resources to do our development on, and also ultimately target for our for the first U.S. exascale systems. So here you see there are certainly more systems in this in the DOE complex, but the systems of note here are reside at the 6 DOE labs that I mentioned before. And the numbers in parentheses denote top 500, the HPL mark as of last November. I guess in about 6 weeks, we'll see another ranking come out at ISC. So these numbers may change, but in particular, we're really fortunate to have Summit, the #1 system in the world here at Oak Ridge, and Sierra at Livermore, #3, and I think 5 of the top 10 in this listing. So ECP is not waiting for the exascale systems, but we're developing and working hard on the current systems and really finding that performance is exceeding expectation with regard to our development work. And we're targeting Aurora, Frontier, and El Capitan. These are the first 3 exascale systems on which we're going to deliver on our metrics, make sure our apps are ready to go, ready to do their challenge problems with certain performance metrics met. So that's and just to highlight 2 systems, the #1 system here at Oak Ridge Summit. I'll talk a little bit more about some of the experiences we've had on this system. Very, very powerful system. 2 IBM Power 9 processors with 6 NVIDIA Volta V100s. Lots of memory, an EDR interconnect, and the system is just now coming into production and will support the Insight program. ECP applications we've been fortunate to work with the OLCF and making sure that our ECP applications have some early access and get some early experiences. And like I said, so far performance is very much exceeding expectations. And as similarly on Sierra, I'll call that a sister system of the Oak Ridge system, #2 on the top 500. A little bit different node footprint, basically 4 Voltas for 2 Power 9s, but for the most part, similar, and we've been able to work closely with our Livermore partners in sharing experiences and lessons learned. Just 2 of the many systems that are important for not just ECP, but DOE writ large. A little bit about the organization, and I think just a couple of comments. We're organized formally as a project, and we kind of look like a small company in that we have a board of directors with our lab directors that oversee our management, execution, and performance. I need to call out a couple of key leaders. Lori Dyson has now been with us for over 6 months and just doing a fantastic job as our deputy director from Lawrence Livermore. We do have an industry council. I'll say a little bit more about that really weighs in on the functional requirements of what we're developing relative to U.S. industry needs, which is very important. Key leadership team shown here. Let me just point out that we have kind of a yin-yang with regard to apps, software, and hardware, in an NSA lab leader, along with an Office of Science lab leader, partnered in co-leading both the 3 main focus areas. And we have a great project management office and project office here at Oak Ridge. This is a large project, and we do execute adhering to formal project management practices, which is new, or at least different for an R&D endeavor, but I think we've kind of figured out how to tailor things in a way that allows us to execute on schedule and on scope. The Industry Council is really important for us. It's not a formal review body, but it's an advisory body led by Dave Kapczynski at GE, and we have a number of U.S. industry companies that have, I would say, are heavily involved in HPC use and HPC development for their businesses, and I'll list them on the next slide. And these folks we meet with a couple of times a year, and they weigh in on, is anything we're doing useful to them? Hopefully it is. Basically, let us know whether what we're tackling will be relevant to them. And overall, our apps and our software we're pushing out and making widely available and accessible. So a number of other industries are certainly interested. This group is giving us kind of an up close and personal opinion as to how we're doing in terms of their perspective. We are organized as a project, and I'm not going to go through the work breakdown structure other than that each one of these level 3 boxes is led by a key DOE lab personnel. These are senior people that are critical to our success. I wanted to be sure and just at least show the names here. Each of these boxes really constitutes a portfolio of 2 to 10 R&D projects. So there's a substantial effort going on in the level 3 boxes. And you know, like I said, there's over 100 of these R&D teams led by principal investigators that are senior leaders in their fields. And so we're really fortunate to have a great leadership team and R&D teams executing our work. Now I want to dive into each of the focus areas, application development, software technology, and hardware integration. And we do have over 20 applications that we're supporting that are DOE mission-centric applications. With regard to application development, let me see if I can advance to the next slide. Okay, so this area is led by Eric Seeger at Argonne, Andrew Siegel at Argonne, and Eric Drager at Livermore. And the overall goal is really to develop new or enhance existing capabilities of applications critical to DOE. So very targeted development of the apps is going on here. We do not have the funds or the time to do major overhauls in many cases, but we are targeting key aspects of the apps. Co-design is very important here, and I'll say a little bit about that. We want to make sure that these apps are ready to tackle very specific challenge problems. And shown there at the bottom is kind of the domain science areas that our applications span, which is really all across most of the DOE mission space. New algorithmic implementations are really required in terms of the application development. So it's not just software redesign, restructure, data design, restructure. It's really rethinking algorithms. In many cases, kind of looking back to the future. Some older algorithms that worked well on vector machines we're revisiting. And so in particular, the implementations involve, you know, how can we reduce communication and data movement, make sure we take advantage of locality and concurrency locally. Where can we cheat, so to speak, and go to reduced or mixed precision to take advantage of hardware acceleration? So this leads to really kind of new algorithms, Monte Carlo versus deterministic, on-the-fly computation versus data lookup. Higher order methods now, we can take advantage of that. Some really nice work going on in a number of these areas. So each application being developed, and it's listed here in these 6 strategic areas, has its own unique plan. Led by a domain scientist that's a leader in the area. Its unique plan is a kind of a unique combination of software development, algorithm development, and implementation. Here you see the kind of the 6 pillars. These applications were chosen in fall of 2016, working very closely with our DOE sponsors, making sure that each application hit a strategic problem of interest to a specific program office. And wasn't easy to select. We had literally hundreds of options, and it was not easy to down select to this 24 that are listed here. And I'm going to quickly go through some of these apps and give you some examples. But before I do that, we've really implemented what I think is an area that's really working, which is to think about applications from the point of view of they typically, each application, although unique in its own area of science, typically has a surprisingly small set of what we'll call computational motifs. In other words, a common pattern of communication and computation. So we've chosen to, in terms of co-design and going after application performance down through the software stack and down to the hardware, we've chosen to go after motifs and really see if we can make those motifs perform well on the exascale and existing pre-exascale systems. So here you see a list of 6 co-design centers and a proxy application effort, and all of them have really been proven their worth, so to speak, with regard to developing not just best practices and lessons learned, but libraries and components that could be, we view as sort of next generation middleware libraries that many applications will use. And the co-design areas span workflow to particles, to adaptive mesh refinement for structured meshes, to unstructured mesh, PD discretization, graph analytics, and scalable machine learning. I won't have time to go through them all, but let me give you some examples. This This co-design effort's focused on an unstructured mesh motif, lots of gather, scatter, indirect addressing, but also with high-order PDE discretization using finite element techniques led by Zanio, Kothe, more known as SEED. And here you see the overall goals and approaches. And this effort's been ongoing, released some new libraries, new capabilities through MFIM and LiveSeed, targeting a number of applications just to show you that this co-design sort of vision is working. SEED has been able to target a number of ECP applications that are very disparate from a domain science point of view, but when you get down into the details, high order finite element discretization and unstructured meshes is what matters. And so SEED and Zanio's efforts really been able to target a number of applications. So this is an important point to make with regard to co-design, that this is an important middleware layer that we're targeting in ECP. Similarly, let's talk about structured meshes and adaptive mesh refinement led by John Bell at Berkeley, known as AMReX, built on a couple of decades of very successful AMR efforts, and not just at Berkeley, but at Livermore and other areas. And so one key aspect here, and John's currently been able to integrate into 5 of our applications, is it's not just AMR, but it's typically a collection of motifs that are very sort of peculiar to these particular applications. So pushing particles on these meshes, solving ODEs, linear solvers, it's a unique capability when you're talking about multiple hierarchies of meshes and embedded boundaries. So John's been releasing his technology and been able to AMReX has been able to be picked up by 5 applications across ECP. Another area is really not traditionally a motif, but we're finding it's so important, which is workflow and online data analysis and reduction, led by Ian Foster at Argonne. And here you see the traditional approach of, an app runs and it dumps its data, then another app later comes in, picks it up and does the analysis. Well, we really can't afford to do that. There's really been a disparity. There is a disparity in the hardware in terms of I/O bandwidth relative to memory bandwidth. And so we really want to be able to do online reduction and, so in other words, the application runs, we're doing reduction of the data as it runs. We're doing analysis of the data as it runs. That analysis may be passive or it could be active back on the application. We might need a couple applications, 2 applications running on the hardware at the same time across different parts of the systems, need to talk back and forth in some sort of non-linearly consistent converged way. So in other words, this is an important motif for us. And this center known as CODAR is also releasing essentially an entire workflow management system that a number of applications, fusion, material science, molecular dynamics, climate are looking at to leverage. Particles really are us, frankly. Particles are ubiquitous in DOE applications and a lot of non-science applications, frankly. The use of discrete particles. This was led formerly by Tim Gurman, now by Stu Miniszewski at Los Alamos. If we look across the DOE application portfolio, we have molecular dynamics, both long range and short range. We have particle and cell for fluids and solids and plasmas, and we have quantum mini body dynamics. And so this is a really potentially large return on investment, is to develop methods to push particles to map particles to meshes, meshes to particles well on a node. This one's very difficult because particles are typically embedded all throughout the application, but we're really seeing some good progress here with a new particle pushing library known as Cabana that we think is going to be able to be leveraged across multiple applications. And finally, another area to highlight, machine learning, in this case, ExaLearn. This is a fairly new effort we stood up last fall, led by Frank Alexander at Brookhaven National Lab. And there are several use cases of interest to ECP. I think obviously we'll be interested in picking up industry frameworks where we can, just leveraging them. So the goal here isn't to recreate good technologies, say like TensorFlow out there. But in particular, we're interested in surrogate models for UQ and error estimation, structure to function relationships, control systems, and inverse problems. And a good example of a very specialized sort of DOE application for machine learning is looking at our experimental facilities. Here's a canonical light source, and I think there are at least 5 in the DOE complex. And these are multi-billion-dollar facilities that are getting great experimental return, but we think we can help even more, everything upstream to the designing the light source beam lines and controlling the beam line real time, to interfacing with the data acquisition system to help understand the data real time as it's acquired, being able to do fast analysis locally on site, and ultimately sending data to the Exascale system, and being able to understand the data and influence the next round of experiments. So this is a potentially high return area. With regard to the Exascale applications, I'm just going to flash through them because I really don't have time to hit, but I just want to give the audience here a sense of the breadth of what we're doing. And so I've listed the PIs and the DOE National Lab. Apologies for the acronyms here. But we have an application focused on turbine wind plant efficiency, and I've listed basically the challenge problem, which is ultimately if the application can utilize Exascale, the specific problem that will be addressed, as well as the challenges with regard to performance and algorithmic development. So each one of these applications, like I said, has a unique development plan with still some sizable challenges ahead. So we have a turbine wind plant application, an additive manufacturing application, an earthquake hazard risk assessment application. And just to give you an example, EQSIM, led by Dave McCallum at Lawrence Berkeley, try and understand and resolve vertical and horizontal motions due to earthquakes. So now you've got a seismic wave propagation application. You want to couple it to a structural application. So you want to be able to capture the ground motions very specifically, and high frequency. And you can't really get to high frequency without Exascale. And you need to get to high frequency to get the structures that matter. Shorter structures and structures related to energy components and nuclear reactors are really important to understand. And so really, Exascale allows you to get to realistic frequencies, couple in with a structural capability. This really represents a good canonical example. One code SW4, finite difference code, fourth order, with a finite deformation code, being coupled in. So a good example of what we're trying to do with our applications is couple multiple physics together. And here's an example of where software extractions, in this case, Raja from Lawrence Livermore, can really extract away some of the complexities of the memory and compute hierarchy, and be able to give you performance almost as good, if not as good, as a hand-tuned, in this case, Kothe implementation for GPUs. So if lower is better here in this graph, and you see that the Raja 4-GPU, 1 GPU implementation is not much worse than a hand-tuned implementation, which gives us a lot of hope that hardware and software extraction layers for hardware coming is a good thing for applications to consider. As we move through our application portfolio, scale up of clean fossil fuel development. This is particle and cell and AMReX with DEM, discrete element methods. Electronic structure with games led by Mark Gordon, catalyst design. Materials for extreme environments. Here you have accelerated molecular dynamics coupled in with a quantum effort known as DFTB to get real-time and using machine learning as well to fit molecular forces for, in this case, materials in fusion and fission reactors. A small modular reactor effort known as ExaSMR. Subsurface, which really focuses on carbon capture, fossil fuel extraction, waste disposal, so it hits multiple DOE program office. Quantum chemistry and quantum materials, and this is led by Paul Kent at Oak Ridge, and really has a number of quantum material applications, from quantum computing to insulators, to superconductors, to storage. And so a fundamental effort that's very going to have overarching effort reach into material science. Let me give an example of what we've done, the ExaSMR effort in terms of Monte Carlo, is an example of overhauling or rethinking an algorithm for the GPUs. In this case, you got a stochastic method, and what the team has done with Steve Hamilton's efforts is to really move from a history-based statistics where you follow each particle independently. That's embarrassing parallel to event-based statistics, where now you're binning particles according to those that might fission, those that absorb, those that are scattered. And by binning particles according to events and not history, you can now get much better utilization of the GPU. And also, instead of reading in cross sections, can you recompute them with something like a window multipole method on the fly? And so here you see they've been able to get much better GPU utilization on Summit by moving to this event-based algorithm, and their overall performance, which is a hard metric for a lot of our applications, has already gone from 15 million particles per second to 600. And so the algorithm development, as history has shown, really outstrips hardware. Other applications, power grid. This is a new non-traditional DOE application that's important for us. Combustion, which is a historically very important application, not just for internal combustion engines, but land-based turbines. This led by Jackie Chen. I'll show an example here. She's building on the AMReX capabilities. This is a great example using our co-design center libraries and components to build an entire new code base. In this case, two codes, Pele C and Pele LM, for explicit and implicit capabilities. And the figure at the top really shows now we can do complicated boundaries by cut cells and embedded boundaries. We can push particles to represent Lagrangian models for diesel spray and soot. And so being able to really leverage the co-design center capabilities and build an entire new application on top. Other applications, Earth system modeling, catalytic conversion of biomass, metagenomics, just to give you an idea of the breadth and depth of what we're doing in ECP. So some very non-traditional applications that are really finding their way into the sweet spot with regard to being ready for exascale. The Earth system modeling framework led by Mark Taylor is really an example of what you can do with accelerated node computing. In this case, he's been able to work hard to implement a subgrid model for clouds, known as a super parameterized model for clouds, and be able to, where clouds are within a cell, is to dive deep, use the GPUs to execute a higher resolution model locally for clouds that doesn't require him to go more globally. So he can use 10 or 12 kilometer resolution for the atmosphere and still go after cloud resolving models locally rather than having to resolve the entire atmosphere at a lower level. We've got fundamental science applications like cosmology, lattice QCD, going after the strong forces, plasma wake field accelerator design. So each one of these points to one or more program offices. And if I had more time, I could dive into other examples here. But just to list them all, whole device modeling of magnetically combined fusion on plasmas. In this case, ITER is a big driver. ExaStar, Dan Kaysen was really critical in part of the LIGO wave determination here about a year ago. So astrophysics, both star mergers as well as supernova. Light source analysis of protein molecular structure and design, that really ExaFEL really ties into linear light source that I mentioned earlier. And a new application that you probably heard of, the cancer moonshot application here, is using card-carrying machine learning to accelerate and translate cancer research. So overall, these applications all have their own unique plan and own unique development plan. But Andrew Siegel and Eric Drager really identified kind of the 6 challenges overall. And these aren't too different from a decade ago. If you dive down, they are different. But making sure the teams port to accelerated-based architectures, exposing additional parallelism and concurrency, and it's a chance to really enrich physics locally. Coupling is a common theme, and so you see the challenges overall that we have in the next 3 years ahead of us. And we really also plan to intensify our efforts to exploit reduced precision representations of hardware accelerated operations, like the tensor cores on the Volta V100s here at Summit in Sierra. Now going to software technology, this is led by Mike Carew at Sandia National Lab and Jonathan Carter at Lawrence Berkeley. Basically, the philosophy here is to be very prudent and extend current technologies wherever possible. Build a comprehensive software stack, but leverage frankly, the hundreds of man years of investment that we already have, and did not recreate, but leverage where possible. Perform new R&D, higher risk R&D where necessary. Integrate carefully with vendors, and that's important. And probably something we haven't done in the DOE as well as we could have, and that's make sure that we have robust, high quality production software. And so the overall effort in the ECP-ST portfolio, really the boxes at the bottom, programming models, runtimes, dev tools, math libraries, and data and viz. Overlaid on that is the ecosystem and delivery piece. So it is an important aspect here is integrating within apps and with our DOE HPC facilities. And so Mike's done a great job in looking across our portfolio and identifying 90 open source scientific products that we've been working on. Some we've created, others or most others we've been adding to. And I'll point you to some reports that can give you more detail, but recognizing that we can encapsulate these products into a smaller set of software development kits that have kind of like products packaged together that are containerized. For example, data analytics and workflows, I/O, math libraries. So he's worked to create an Exascale scientific software kit, and I'll mention that a little bit later with regard to the repository for these SDKs. That we are really working hard to push out these products on a regular basis, at the very least, kind of every 6 months. Working hard to leverage best practices as well with U.S. industry and vendors in particular. So here's kind of a bar chart, or it's a little bit detailed, but gives you an idea of the efforts in ECP in terms of software technology, programming models and runtimes, dev tools, math libraries, data and viz, and software ecosystem. And not surprisingly, the programming models, we're really tackling MPI and OpenMP, also PGAS languages and some task-based runtime models, Legion, Parsec as an example. The dev tools, really important to work hard to push our compiler technology effort for the most part through LLVM, but also having debugging and performance analysis tools as well. Linear algebra, almost all of our apps in the end, distill down into linear algebra. We have a sizable effort there, and probably the most mature effort that's really key for our application efforts. And just to kind of jump over to the software ecosystem, recognizing that we need to package, containerize, and deploy these products on the HPC systems is really important. An example, really just one example of one of the many milestones that comes out of our efforts. And this is, so a milestone in ECP could constitute a release, a technical report, a demonstration simulation, performance analysis. This is just one example of, investigating the use of reduced precision integers and hyper, going from 64 to 32-bit integer, trying to take advantage of the accelerated hardware on reduced precision, in this case seeing about a 25% performance increase just by investigating where can we go to lower precision and still do the job. So just wanted to point out that we are a project with milestones kind of every 3 or 4 months, and this is a good example of a hyper milestone. Mike Carew likes to point out, and we totally agree, that it's important for ECP software technology staff to be part of standards groups. So the end game is not more complicated software extractions, but really to work hard with the standards group to see those abstractions that are working to find their ways into standards. And the HPC community really needs to be at the table when these standards bodies get together. So we have heavy participation in these bodies. And so far, we've seen it really bear fruit with regard to many of our efforts finding their way into standards, and most recently being LLVM and the FLANG effort. So Mike has put together a comprehensive report, and I have a website I can point you to. This is just a few excerpts from that report that show all the products being developed in ECP, pointers to the open source repositories. So lots of products coming out of ST, and we're working hard to package them into a half dozen or so software development kits that are already on our website, known as E4S. They really are a key delivery vehicle for ECP. We're finding that by the community get together and agreeing on a set of policies and attributes for these SDKs, that's a good way to not just work together with an ECP, but work with vendors, the facilities, and even international efforts as well. And so it's really a great way to bring together multiple bodies in terms of deployment. A good example is the Math SDK that Mike and his team really have been pushing really before ECP started. But this SDK, known as Exascale, here's an example with the green bubbles of the math libraries many of you probably will recognize that were embodied within Exascale December 2017. And now you look at 2018 and you see we have more green bubbles brought in. And this allows as an application developer myself, allows almost, there's nothing maybe quite like plug and play, but almost like plug and play, to be able to bring an SDK into your application and try out different solvers. And it's really a good way for the solvers to frankly compete with one another. A given application can try different options and really be able to sleuth out the best possibilities with regard to performance. So for the crowd on here, please do follow these development efforts. In particular, we plan to refresh these SDKs on a regular basis, and you can see the plan moving forward, which is to have not just an XSDK, the yellow on the far left with the math, but programming models and runtimes, tools and technologies, compilers and support, biz analysis and reduction, and data management and I/O. So we're working, I believe right now, 4 different containers are going to be supported: Docker, Singularity, Charlie Cloud, and I forgot the last one. In any case, I think on my next slide I give the website. Summer State University of Oregon's done a great job in helping us to deploy this material on the website. We've gone through 2 releases so far, and we should see not only the maturity and the production quality of a given product get better with time, but also the number of products increase. And our primary focus is our DOE HPC facilities. And I mentioned the 6 labs also all have DOE HPC centers. We have NERSC and OLCF and ALCF, as well as our 3 NNSA labs. But we are interested in the folks here online in the industry and university pulling down this material, giving it a test run, giving us feedback on what's working, and more importantly, what's not. So again, lots of products out there. We've been using SPAC, developed by Todd Gamlin at Livermore, to build the products, finding that to be very, very useful. And so I encourage the audience here to take a look. And we have packaged together in one capability assessment report, or CAR, kind of in 6-month refresh cycles, a comprehensive write-up on all the software technology effort going on inside of ST. So encourage folks to take a look at that and let us know what you think. Moving on to the third area, hardware and integration. This really supports U.S. vendor HPC research, but also make sure that the SDKs we're developing are deployed on facilities that does that formal handshake, as well as works closely with our applications and performance engineers who are really close to the hardware, trying to eke out that last bit of performance on our apps. Our Path Forward effort, which started in 2017, has been funding node and system R&D for these 6 vendors listed here. It's a sizable program. It's part of ECP, and really been instrumental in positioning these hardware vendors for making nice exascale offerings. Examples of the work funded include memory architectures, higher speed interconnects, reliability, innovations for increased parallelism, and reducing the power requirements. So this has really been a program that's paid off. We expect to see this program come to an end with an ECP within the next year and a half. It needs to be upstream of the exascale offerings, and this is a notional sort of picture, which is we want to accelerate the hardware innovations in terms of multiple work packages for each of these vendors. Really, we want to see this work productized in terms of hardware innovations that ultimately appear in exascale system deliveries. We're very confident we're on a good path to see this happen. And then once the systems have been selected, further NRE funds are not part of this project, but we will be part of the procurement projects to reduce risk in the ultimate systems that are deployed. That's a key aspect of hardware integration in ECP. Another one is to, it's not enough just to have a development team working on an application, kind of thinking about hardware. They need to have very specific focus on specific systems and abstract that away to the extent they can to remain portable. And here is where we're working closely with our HPC facilities in really funding their performance engineers who look at our applications and really work hard to make sure, in particular, the node performance is very much tuned to to the hardware on the floor, and working closely with vendor centers of excellence. We the facilities have had great experience for the last decade or so in getting across the finish line with regard to application performance, and we expect that to happen here in ECP. I mentioned the SDKs. We want to really make sure that we have a seamless process for pulling down our SDKs from say, the e4s.io website and deploying them in a seamless, continuous integration fashion on the facilities. And this is a sort of formal handshake between our hardware and integration effort and our facilities. And this is something we haven't done well in the past, as I mentioned, to really develop good, hardened production quality software components. And that's been a key aspect of the ECP goals here. Kind of a notion, more than a notional picture of this. And this area is led by Terry Quinn, by the way, at Lawrence Livermore, and Susan Coughlin at Argonne National Lab. Is, if I'm a software developer on one of Mike's software products, the SDK process ought to see a mod that I've made, committed, pulled it into the SDK, packaged it up into a GitLab site, in this case DOE OSCE Center, and then there should be a seamless process for basically punching through firewalls and pushing these latest SDKs down into the facilities in a production sense, and get continuous feedback on, has my mod broken something on Aurora or Frontier or Summit. And so we want to make sure this process is in place now and really streamlined and working well prior to the Exascale system. So this formal handshake is something kind of new that we're just standing up. We're quite excited about. So this gives an example of sort of our view of ECP's flow of software and application delivery. We start with our software products. There are order 90 of them, package them into SDKs, order a half dozen, make sure there's APIs for the SDKs that are cognizant of the applications and really driven by application requirements. Really embrace agile development to where we're doing, pushing out the SDKs early and often, continuously integrating, testing, getting feedback on what's working, what's not working, and ultimately deploy on not just the first 3 exascale system movers, Aurora, Frontier, and El Capitan, but the pre-exascale systems as well. So this infrastructure is in the process of being put in place right now. So just to summarize, we do have very specific performance metrics, and I didn't mention that our target to complete ECP is 2023. We feel like we're well on track to do that, and the leave behind, we're not going to just disappear and walk away. Our sustainable products, applications, and a software stack and an ecosystem, and we believe we're on track in our 3 critical focus areas: applications, software stack, and hardware and integration. I need to really thank the team, and in particular, our Department of Energy Support and Leadership, Barb Helen, the Oscar Associate Director and ECP Program Manager in the Office of Science, and Took Hong, the Advanced Simulation and Computing Program Manager in NSA, and our site office management, Dan Hogue here at Oak Ridge and Sam Brinker at Lawrence Livermore. It's a very complicated project. We get lots of help and support from our DOE sponsors. I'd be remiss if I didn't acknowledge them, as well as, let me point out the senior leaders. I mentioned we have lots of fantastic folks. We have about 30 level 3 and level 2 leadership. Here I've listed the level 2, and I mentioned names: Lori Dyson, our deputy, Andrew Siegel and Eric Drager, leading our applications effort, Mike Carew, Jonathan Carter, our software technology effort, and Terry Quinn and Susan Coughlin, our hardware and integration effort. That said, apologies for talking so fast. I'm very excited about this project, and probably showed. I also need a drink of water, so I'm going to pass it back to John in case we have any time for questions.
Doug, thanks. That was a great talk. Drink fast, because we do have some questions.
Okay.
The first one we've got is, so how do you build an effective exascale software stack if you don't yet know the architecture of the systems that you're building for?
Yeah, that's certainly a risk, John. I would say that because of our Path Forward effort, we are fairly intimately involved with some of their developments and have a decent line of sight into potential products. So while it doesn't reduce the risk and allow us to laser focus, we're not just shooting in the dark either. I think the team has a pretty good idea for the targets of opportunity, but we will, as a project, we will know these details very soon. And again, the procurement projects are not part of ECP, but we're not going to be running much longer without knowing the details.
Okay. So we've gotten several questions along the lines of the following. So there are undoubtedly a lot of people in computing attending today that aren't from DOE and maybe won't ever use an exascale computer. Do you think, given that ECP is developing technologies that might still benefit those people that maybe won't use Aurora or Frontier directly?
Gosh, it's a great question, and I should have addressed that directly before, John. All of our application and software development, and I'm pretty confident in saying all of it, happens initially and frankly continuously just on a laptop or a desktop. The first thing you need to do is to really figure out how to utilize a single node, and most of even these exascale systems, most of these single nodes don't look too dissimilar from even a laptop or a high-end desktop. That said, when you're talking about scalability and performance on a larger system, you do need to test and debug and develop on a larger system. But we would be irresponsible if our applications and software stack, frankly, can't function at some level on a laptop and a desktop. And often, as I'm sure you're well aware, John, you make performance improvements, with an eye toward exascale or a particular exascale node, and you find out that things work better on your laptop as well. So all of our technologies really are designed with the idea that they need to execute on the whole suite of hardware available. So this does not preclude anyone out here from investigating our software stack or a given app for a much more modest simulation. That's an important part of our scientific workflow as well. We just don't do big exascale calculations. We do the whole suite. Okay,
great. So this question surprised me a little bit, but we've actually gotten it several times, and I'm happy to see it. It seems like there are at least a few people in the audience who are interested in making HPC a career. Maybe they're already doing it and looking for a move. Is the ECP hiring?
Yes, we always are. One of our risks, John, is recruiting and retention. I will say this, that we've been able to recruit some of the best and brightest. I think we do have the best and brightest. But you know what? We train people very well, expose them to the best tools in the world, frankly, and fantastic community, and everyone is pretty marketable. I'm not saying people are looking to run away, but we're fortunate with our DOE sponsors to have a very stable funding profile, and we are always hiring. And I would also note, for those who are interested in this area, that we do have an active training activity, and you can go on our website, and most of our training, which we designed to kind of help ourselves, so to speak, really I think is more broadly applicable. And there are videos and seminars to tap into there. So I encourage folks interested, they can just go to our website and kind of see what we're doing. But I also put names in here, so folks who are interested in joining ECP, or at least want to explore that possibility, can feel free to contact any one of us.
Okay, great, thanks. I think maybe we have time for just one more quick comment, and then we'll wrap up. But I'm interested in the answer to this myself. How did you decide on the application portfolio that you're working on in ECP?
Very good question. I was heavily involved in that, John. It was not easy. I'll just say this. The main driver for those selections were DOE mission need, and so solving or tackling consequential problems of mission importance really drove the selection. And I'll just point out that if we selected the applications that were lowest risk, it wouldn't have been this set. We have some higher risk applications. That doesn't mean we're going to fail, but we have a heavy lift with this development. The other thing, too, is each application is pursuing a specific challenge problem. I call it a challenge as opposed to a grand challenge because grand challenge to me often means we never get there. Each application has a specific challenge problem negotiated with a stakeholder program office. And this challenge problem is one that's of strategic importance to the office. It's one that's currently intractable with regard to compute resources. And I guess kind of stating the obvious, it's one that's amenable to a computational or data science solution. So an important driver for this portfolio was DOE mission need. And I didn't mention this, John, but there are 10 program offices in the Department of Energy that we targeted with these 24 applications. And so, frankly, we were interested in many, many more, but had to down select, and it wasn't easy. But if you kind of do the math, it's kind of 1 to 3 applications per program office. So not many, but I will add that the expectation is these applications will be more generally applicable to a general class of problems. They're not going to be boutique apps for one problem on one hardware. So we've negotiated closely with the program offices to make sure that the development's going well and that it's going to be more generally applicable, with a challenge problem being, not just a demonstration, but a key problem we want to tackle, on day one when the Exascale systems show up.
Right. Well, Doug, this has been a fantastic talk and great answers as well. I want to thank you for taking the time to do it, and I want to thank each of the attendees as well for taking the time to attend and submit great questions. Let me say that there were a lot of questions we didn't get to. We're going to make every effort to answer those, and when we let you know about the archive video going up, we'll provide a link to the answers to those questions as well. So as I've mentioned a few times, this Tech Talk has been recorded, will be available online. You can find announcements on upcoming talks and other ACM activities at learning.acm.org and at acm.org, of course. Also, I really want to encourage you to fill out our quick survey. It helps us pick future topics and speakers, and also helps us make sure that what we're doing is of interest to you. So on behalf of ACM, SIG HPC, and Doug Kothe, thanks again for joining us, and I hope you'll join us again in the future.
Thanks, John. Thanks, everybody.